pleasure to introduce Professor Chris Parry today from the University of Exeter. Chris is the Director of Research at the School of Geography there in Exeter. Prior to that, he was at Manchester University, where I first got to know him. Chris works on geomorphology and sedimentology and carbonate budget work. A lot of it looking into sort of historical perspectives, but also looking at modern day response to environmental change. He's also, aside from myself and Dave Bellwood, one of the few Corrie scientists with a northern accent, so probably don't understand him. But Chris does a lot of work here in Australia. He works with Scott Smithers a lot. They're going out on the Kirby tomorrow to do some more research. He also does a great deal of his work in the Caribbean, and that's what he's going to be talking to us about today.
All right. Thank you very much, Nick, and it's a great pleasure to be here. Thanks very much for coming along. I'm going to talk today about some work that we've been developing over the last, I guess, about 4 or 5 years now, which is looking at the effects of ecological decline, reef ecological decline, on rates of reef carbonate production, and thinking about what that means for future reef trajectories and reef growth potential now and into the future. So I'm going to provide an overview of sort of what we've been doing and why, a little bit about how we've been doing that, and then some of the work that's recently come out and some work that's sort of emerging at the moment as the range of sites we've got data from slowly kind of expands. This is an interesting audience to come and speak to in terms of how to present and start one's talk. I don't really need to spend an awful lot of time talking to an audience like this about the kind of issues affecting reefs globally. We all know about declining live coral cover, increases in macroalgal cover, and progressive deterioration in reef structural complexity on many reefs, and of course there's data sets globally and regionally that emphasise these kind of trends. So I'm not going to spend very much time talking about that. It's probably worthwhile spending a little bit of time, however, talking about the Caribbean, although I've been informed last night that there's obviously a Caribbean workshop taking place here, so a large proportion of the audience will also know an awful lot about what's going on in the Caribbean. But for the benefit of those who haven't worked in the region, I think a short introduction is probably useful. It is arguably the region that's undergone probably some of the most dramatic and I think regionally consistent changes in reef ecology, at least since the 1970s, and I say at least, and this is of course reference partly to Jeremy's work that showed that actually probably the history of disturbance in the region predates a lot of our sort of surveying efforts in terms of fishing pressure and so on. But of course there are lots of data sets that have been published that show declines in live coral cover since surveying efforts started in the sort of mid-1970s, and associated with that very significant declines at many sites in terms of reef rugosity, reef structural complexity. And of course, much of that in the region has been driven by the impacts and decline of the acropora corals, the Elkhorn coral, Acropora palmata over here. And if you go to kind of previously palmata-dominated habitats at all sorts of places around the Caribbean, this is pretty much what you see, remnant stumps and colonies and sites with much lower topographic complexity. Lots of bio-eroding sponges starting to come in and colonise a lot of the substrate in many areas. And slightly deeper depths in many sites. We've also lost the staghorn coral, Acropora cervicornis. This is a photograph from Discovery Bay in the late 1960s. And again, if you go to those sorts of habitats today, this is pretty much what you see. Lots and lots of Acropora debris, some remnant Montastria or Orbicella, as we should call it now, colonies, and then various types of sort of more opportunistic or weedy taxa coming in and colonising those degraded framework surfaces. And we see evidence for that all over the place. The factors that have driven these declines, of course, are also very well documented. Some are site-specific, but there have been some key regional drivers. Obviously, the diadema die-off in 1983 caused major changes in Caribbean reef ecology, and the diadema have really failed to recover. There's a little bit of recovery perhaps at some sites and a few pockets where they remain abundant, but generally you really see very few of those key substrate grazers in many areas. There have been various bleaching episodes, of course, associated with sea surface temperature anomalies. And then some really key disease events that have affected the acroporas, but also some of the more massive coral taxa as well. And so these have been superimposed on a very long term fisheries overexploitation. And so I make the point here, it almost certainly had already changed reef ecology prior to what might regard as our sort of relatively recent monitoring efforts. And of course, Jeremy's written extensively about some of these changes in the past. So those are the big drivers. The consequences, well, there are two major consequences, I suppose, in terms of the benthic ecology. One is exemplified by the sorts of transitions that we've seen in places like Discovery Bay in Jamaica, with coral cover declining very, very dramatically, bottoming out at perhaps a few percent and really sort of flatlining, and associated with that fairly large increases in macroalgal cover. So there's some nice photos I stole from the web here that show kind of Discovery Bay in the 1970s and sort of same sorts of sites on the Reef today. Worryingly, perhaps many of the massive taxa that remain, the kind of key reef framework building species, are also being progressively affected by disease in many parts of the Caribbean. Less so perhaps in some areas in the southeast, which I'll talk a little bit about later on. But nonetheless, the major historically important and recent geologically important reef frame building species have been very, very heavily hit.
What's the source of the graph in the upper left?
That's one that I put together from a paper that was in Coral Reefs in 2008, so it was sourced from various published data sets. Little and Olhurst type work. And
Caribbean wine?
No, that's for Discovery Bay.
That's for Discovery Bay.
Yeah.
Well, I'd love to see that.
So what we've seen at many sites is a kind of progressive increase in certainly in relative abundance, but perhaps at some sites in terms of absolute abundance, it's difficult to say at some of those sites because of the lack of pre-existing baseline data in what have been described as sort of more weedy or opportunistic species. And so there are some nice core records from various sites that show, as far as we can tell, that these sort of transitions are unprecedented, certainly in a late Holocene context. This is from Belize, that show kind of a cervicornis dominated sequence with Agaricea tenuifolia coming in and dominating the upper parts of the horizon there. And so, as far as we can tell, we haven't seen changes of this scale, and certainly over these spatial scales, at least in the last few hundred and perhaps a few thousand years within the region. And so this is obviously changing the nature of the benthic ecology. It's changing the physical structural complexity of the reefs. It means that we have an emergence of taxa coming in that probably grow much more slowly and therefore producing less kind of carbonate. So I think what we can say is that we know quite a lot about the causes, we know about the timing, and there's plenty of kind of large spatial scale studies from the Caribbean that indicate that we know quite a lot about reef ecological decline. What we know much less about is what the impacts are in terms of the physical resilience of the reef structures and about reef growth potential. Perhaps in some ways the impacts are a little bit intuitive, but we lack any real quantitative data on what these changes are doing in terms of the rates at which reefs are producing and accumulating carbonate. And I think there are two particularly pertinent questions here. When and how quickly do these ecological shifts, so what we might think of as unhealthy states, how quickly are they manifested in terms of a change in the carbonate production regime, and what happens to reef growth potential under different ecological states and scenarios of change. And I think what we need to remember here is that reef growth is of course a function not only of the rates at which corals grow, but of also the rates at which other key carbonate producing but also eroding processes operate. And so in order to understand and get a handle on some of these questions, we need to kind of integrate assessments of these processes, the rates at which they operate, into surveying and monitoring efforts. So the kind of carbonate budget assessment approach that's been variously tried in a number of different places historically, and which we're now trying to sort of develop more extensively across the region. And those questions, of course, have very wide-ranging relevance. We can link a lot of them to kind of ideas around ecosystem services, ecosystem service provision. They affect the ability of reefs to maintain their structures and their structural complexity. And so, of course, that has obvious implications for fisheries and so on. It's been very well described and by a number of people, including Nick, of course. But of course, they also influence the ability of reefs to track sea level rise. Mid-range, high probability estimates of perhaps 3/4 of a metre sea level rise by the end of the century persist in the IPCC reports. And of course, we're not talking about reef drowning here. We're not talking about submergence and loss of reefs, but even relatively small-scale rises in sea level that reefs can't keep pace with will have important implications in terms of shoreline protection because of increased wave overtopping. It will potentially change habitat functionality within the lagoon areas and so on. So there are lots of reasons why understanding growth potential and carbonate production regimes I think are really, really quite important. So a carbonate budget, what is it and how do we kind of try to calculate one? It's essentially a measure of the net rate of carbonate production on a reef. And so here we need to obviously take account of the obvious biological framework producers, of which corals are obviously major drivers. And of course different coral species grow and calcify at different rates, so we need to have ways of taking account of that. There are also relatively large amounts of carbonate produced by calcareous algae, coralline algae, which are important framework binders, but also can produce reasonably large amounts of carbonate and often ubiquitous on substrates, even underneath a lot of the macroalgal cover that you see covering many Caribbean reefs. If you dig around under that, a lot of it has coralline algae that appears to be living, perhaps calcifying at a slower rate, don't know, but there's nonetheless a lot of that material on a lot of the Caribbean reefs still. And set against that, we also need to think about some of the key biological carbonate eroding processes. The bioeroders, things like the parrotfish, the urchins such as diadema, the endolithic sponges, the microborers, all of these things that act to denude the actively producing carbonate on the reef and either convert it to sediment or directly dissolve it. So these are biological drivers of production that we're largely talking about here. And so in an actively accreting reef environment, production will typically exceed or will exceed the rate of erosion. And although you might have fairly high rates of erosion by parrotfish and urchins and sponges, those are lower than the rates at which corals and coral algae are producing carbonate. So the net budget in this sort of simple cartoon here is obviously positive. Conversely, in a non-accreting reef, production will either be equal to or less than erosion. And so although you may still have some production from corals and corallines and so on, those are exceeded by the rates at which parrotfish, urchins and so on are eroding the substrate. So again, in this simple cartoon, we have a negative budget. What we have to remember, of course, in terms of reef growth and so on, is that a lot of what is produced is often exported off the reef or it's reincorporated as sediment. And that's quite a tricky kind of thing to get a handle on. But if we're interested in reef growth, we really need to also address the issues of sediment production and the physical removal of reef-derived carbonate. It's very clear if you go to, this is actually from the Maldives, but there are plenty of examples on the GBR, that reefs produce and reincorporate or export very, very large amounts of sediment. Large reef islands sitting on relatively small reef platforms. It illustrates very clearly the very large amounts of sediment that they can produce and deposit in noble locations. Most reef environments will also export an awful lot of potential framework carbonate. These are some fantastic shingle ridges dominated by copper and so on up on Piping Island in the northern GBR. And you only have to look at the vast amounts of carbonate that are being pruned off the shallow forereef environments during cyclone events to kind of realise how much is potentially missing from the geological record in terms of the kind of reef growth history. So these are very, very difficult things to factor into budget calculations, but they're really quite important in terms of kind of linking what's going on biologically to sort of longer term reef growth potential. So we need to think about these things, but what I'll do is I'll sort of park that idea for the moment, and I'm going to talk a little bit about the kind of biologically driven process work that we've been doing, but I'll come back to some of these ideas a little bit later on in the talk. So I've been leading over the last 4 or 5 years a project called Reef Budget, which was designed to basically develop a sort of census-based approach to estimating rates of reef carbonate production, which came out of a UK Leverhulme Trust International Research Network, which also involved Pete Mumby, who was at Exeter at the time, but obviously now at UQ, Scott Smithers from here, Paul Kench at Auckland, Evan Ediger at Memorial in Canada, and then Bob Stenek at Maine. So we had a number of workshops and field expeditions associated with that. But the underlying rationale is kind of based on this conceptual paper that we put out in 2008 in Coral Reefs, which had a diagram that looked rather like this, which sort of envisaged reefs existing in this sort of ternary space, depending on rates of production and erosion. And I used at the time the term net accretion and net erosion. I think actually what we should probably have had in here was positive production state and a negative production state, because for the reasons I've just outlined, there are other factors that need thinking about in here that have a bearing on accretion as opposed to production. But nonetheless, that was the kind of framework, and we spent time really trying to utilise and develop established and therefore relatively acceptable survey methodologies and adapt those to allow us to make some estimates of rates of carbonate production and erosion in different environments. So the way that we do this, we in terms of estimating rates of production, we census benthic cover and surface rugosity data. We use a modified version of the line intercept method, whereby we actually measure what's going on over the true three-dimensional surface area of the reef, and the benefits of that have been outlined in a paper that came out of the COE, the Gopi and Bellwood paper in 2011. But we use basically a flexible tape underneath a master line to survey and measure the surface cover by all key taxa along those areas. And then that data is combined with measures of density and linear growth rate to yield a carbonate production rate relative to the true three-dimensional surface area of the reef. We've made this available through our website, and you can download all the various spreadsheets and data sets that go with this. It's preset with kind of regional averages in terms of density and linear extension and so on, but it's entirely user changeable, so you can adapt it and use it with rates that are specific to your site if you have them, or if you've got new data, you can utilise those as well. It's only set up at the moment for the Caribbean. We're developing similar stuff at the moment for the Indian Ocean, which should be available relatively soon. And so what's on there? A series of spreadsheets. We've used Excel for this just because it's readily available for almost everybody. And you input various substrate codes and the linear distance, and there are all sorts of metrics that come out of this, lots of data on contributions by different coral taxa and so on. But what it generates is some estimates of rates of carbonate production, and some rugosity measures and so on here. So as I say, only for the Caribbean at the moment, which is mainly where we've been working, but we're also doing some of this work now in the Indian Ocean, and those sort of approaches will be available soon. In terms of urchin erosion rates, we do censuses along these lines, along an area half a metre either side of each line, looking at species, numbers, sizes, and then we relate these to kind of published, established relationships between urchin size and erosion rate, and you can either do that in a sort of general way, or there is enough data really, particularly for the Caribbean, that you can do this at the sort of species level. For parrotfish, we do belt transect surveys, again looking at species, life phase and size along these, and then use established relationships in terms of bite rates, mass eroded, and so on to generate estimates of rates of parrotfish bioerosion. Endolithic bioerosion is a little bit more problematic to deal with. It's difficult. We've used a sort of adapted version of the non-destructive method that Ward Page and co-workers produced, working in Florida, where we do a kind of census of the surface area that's covered by endolithic sponge tissue, quite time-consuming survey work, but again, develop some relationships in terms of coverage of endolithic sponges and then rates of erosion. And that work will also be enhanced a little bit fairly soon. We've been working on different types of cleonid sponges to develop some individual relationships for those. So that work will develop a little bit more. And then probably the most problematic to deal with are the endolithic microborers, which are of course too small to do any possible census work with, but I think it's not a process that can be ignored, because the published rates from experimental studies are fairly significant. And so what we do is we use published rates for different water depths and then apply those to all available area that can be potentially colonised by endoliths as one way of trying to factor in that key process. So those are the main things that we kind of look at, and the ways in which we've so far been sensing these different processes. All of them are in a kind of state of progressive refinement. But to come back to I guess one of the kind of major questions, what does ecological change mean for reef carbonate production and reef growth? What we did during the initial phases of the Reef Budget project was to work in 4 different countries in the Caribbean. We worked in Belize, Grand Cayman, Eleuthera in the Bahamas, and then in Bonaire, working within a range of kind of common Caribbean 4 reef environments. We worked on 22 individual reefs around the region, and data from 122 transects in these areas. And on those reefs, well, I think ecological condition kind of typifies the spectrum of states that you see in many areas of the Caribbean. If you look at the sort of metadata that's been published on this, on most reef life, coral cover is very low, less than 20%, and often markedly below that. Most sites had very, very low cover of living acropora, and in most cases there was none. Although there is sort of evidence from most of the places that you go to in the Caribbean now for perhaps some very small scale recovery. I mean, most places we've seen small acropora colonies of Palmata and cervicornis. There's not a great deal of it, but they're clearly new recruits that are reaching these sorts of kind of sizes. Mackerel cover often very, very high, and of course substrate grazers in most areas, the urchins and the parrotfish were very, very low. Bonaire was a notable exception. Coral cover, certainly within the protected no-dive areas in Bonaire that we were able to go and access, is pretty good. It's around 40%, lots of large Orchella colonies, thus far unaffected by disease, lots of madrassis, as you can see here, a few Palmata colonies in the shallow areas, and so a bit different in those areas to many other areas of the Caribbean, and that kind of fits with some of the kind of published work on some slight differences in that part of the Caribbean region at the moment. In terms of regional carbonate production rates, what this plot shows here are the net rates of production in black, and then gross rates of production in the white, and in the grey, gross rates of erosion for each of the sites that we looked at. Net production rates across our sites range from about minus 1.7 to plus 9.5 G, so G is kilograms of calcium carbonate per metre squared per year. Some of you may have seen some of this work that came out late last year. Belize, Grand Cayman and the Bahamas, net production rates typically very, very low. About 21% of those reefs had net negative budgets, according to our calculations, in the range of minus 1 to minus 0.1 G. 26% of the sites had positive net production figures, but still less than 1 G. And only 5% of the reefs in the study had rates perhaps anywhere close to perhaps what we might expect for relatively good reef sites. So these are the very low sites: Belize, Grand Cayman, Eleuthera. As I say, Bonaire was a notable exception, had the highest production rates that we found, certainly within the no-dive reserve areas in Bonaire, at depths of 5 metres, about plus 3, and in the 10-metre side, depths of about plus 9. Also very, very highly rugose reefs, particularly at the 10-metre side, rugosity measures of about 3 to 3.5, which is about as high as you'll probably find anywhere in the Caribbean at the moment. There was significant variability within and between habitats. Within the Orchella spur and groove habitats, typically had the highest G values overall, means of about 3, and all others had G values of less than 1.5. I always forget when I show these silly things on. But significant intra-regional variability as well. So net production rates in the Orchella spur and groove type habitats in Bonaire significantly higher than in comparable habitats in Belize and Grand Cayman. And the same kind of picture for the very shallow water Palmata habitats, but not significantly different. So there's a great deal of variability. It's not we don't have massive amounts of replication within habitats for this stage of the study. But nonetheless, it's quite clear that there are some sorts of fairly interesting differences within habitats and between habitats across the region. What are the implications in terms of assessing reef health? Well, there's a fairly strong and significant relationship between live coral cover and overall G values. So these are for the different habitats at different sites across the region. If you look at all of that data, it suggests on average that production states, overall net budget states, become negative or start with zero or become negative when coral cover falls below about 10%. Now, that's I would say is a sort of threshold figure because it obviously depends on the types of coral taxa that you have present in the site, and it also depends on the abundance of the bioeroding species. But it provides an indication at the point at which the budgets in our studies showed evidence of tipping into states of either stasis or net erosion. I think there's always a slight danger of putting out those sorts of numbers because people always jump on them as a figure, so we were fairly careful to try and highlight that as a kind of threshold figure. But I think the key point is that obviously given the very low coral cover that we see on most reefs, that many Caribbean reefs are probably very close to being or are already in states of either stasis, neutrality in terms of production, or potentially moving into states of perhaps net negative production. The interesting question that we've also tried to think about here, and it comes back to some of the points that I was making about the need to incorporate sediment production and so on into estimates of reef growth. We've tried to, as far as we can, to make some considerations of what this means in terms of changes compared to historical rates in terms of coral reef growth potential. So we factored into converted our production rates. We took some factored for framework porosity as derived from core records and sediment reincorporation rates from some of Dennis Hubbard's work in the Caribbean, and then compared the rates of contemporary production with those that can be derived from depth equivalent intervals in the Holocene core record from the Caribbean. And that's quite an extensive core record from 12 different sites, and so we divided this up into sites of less than 5 to 10, and then greater than 10 metres. And so what these plots on the right show here, in the light blue is the percentage abundance of sites with different accretion rates through the Holocene for the shallow 5 to 10 and the greater than 10 metre sites. And then in the darker blue are the equivalent rates that we've calculated. Coming back to the point that I made earlier, I'd say that the rates we've calculated here are probably fairly optimistic because it's very difficult to factor for periodic removal of framework carbonate, which will obviously be incorporated within the long-term Holocene averages. But even though they're probably fairly optimistic, net rates of production or net rates of growth today compared to those that we've seen in the Holocene are very, very significantly reduced. The highest end rates, or the high end rates that we calculate are actually fairly comparable to the very highest rates of accretion recorded in the Holocene in the Caribbean from Alcan Reef in Mexico. It's about 12 millimetres a year accretion rate. But overall, they've... Oh, what have I done here? What have I done here? There we go. Too many buttons. But overall, very, very low in historical terms. So the Palmada habitats, average Holocene accretion rates, nearly an order of magnitude higher than the modern, so 3.6 compared with 0.68, and in the Orbicella spur and groove habitats, about 50% lower today than those rates that were calculated through the Holocene. So this points to some fairly substantial changes with some fairly significant implications in terms of future reef growth potential. So what are the kind of key points that we can draw from this? Very strong evidence the ecological decline, I think, is suppressing rates of reef carbonate production. Perhaps an intuitive point, but one for which we've not really had any quantitative data in the past. So we're able to kind of add some numbers to that sort of story. On average, current production rates are reduced by at least 50%, probably compared to historical rates, so those in the core records. And many of the sites that we looked at are probably starting to shift into net erosional conditions. Calculated accretion rates for the shallow core reef habitats close to an order of magnitude lower than the Holocene, and they may well be even lower. I think, as I say, we've probably been fairly optimistic in some of the calculations that we've produced. And a live coral cover threshold of around about 10% appears fairly critical for any attempt to sort of maintain a positive production state. So that's all very interesting. I think there are two other interesting questions that I'll briefly touch upon here that are relevant here. And those are questions around, well, having lost a lot of the key framework builders from the Caribbean, the Acropora, and a lot of the Montastria, or Orbicella, sorry, need to get into the habit of calling it Orbicella, it's still stuck with the old terminology. What are the main coral taxa now driving carbonate production rates in the Caribbean? And I guess given that the rates are so low, why have more widespread transitions to very net negative states not occurred? To address the first of those, regarding carbonate production, well, as I said, we know that most of the historically important and certainly recent geologically important frame builders have gone, and instead what we've started to see is this sort of emergence of opportunistic, weedy coral taxa at many sites. So things like varieties, asteroides, Agaristides, Siderastria, Millipora, coming in and colonising a lot of these degraded reef substrate surface. So these are fast-growing, relatively short-lived taxa that have either increased, certainly in relative terms, at most sites, and some sites perhaps also in absolute terms. And in terms of the future, well, there's been some interesting ideas put out by people like Cote and Darling around perhaps these species having greater resilience to future disturbance regimes and potentially kind of dominating within the region in the future. So it's pertinent to think about what this means in terms of carbonate production. We can address this particular question with a much expanded data set from across the Caribbean, which integrates not only our original sites from Belize, Cayman, Bahamas and Bonaire, but a whole series of data that's come from the Antilles that Bob Stennock's been collecting as part of his recent expedition in this area. So we now have data from 17 countries and islands, 74 individual reefs, and 336 transects around the region. So this is now turning into quite a nice kind of data set, which we've divided up into different depth regimes around the region. Primarily because I'm still trying to extract habitat data from Bob, along with his depth data. So at the moment we're working with these on a depth basis. So this is quite an exciting data set, really. And if we look at what these plots here show is the abundance of different coral taxa on these reefs. So I'm showing Acropora, Orbicella, collectively the opportunistic species and then others. And the opportunistics are shown in the black bars here. And you can see that these are extremely abundant on all of the reefs. The relative abundance of these corals is very significant at all of the sites that we've looked at. They comprise the highest proportion of the coral assemblage at over 70% of these sites, and they constitute more than 50% of the coral assemblage at about 60% of the sites, so 44 of the 74 reefs that we've looked at. It's also the exception where the opportunistic species are not now the major carbonate producers. And shown in this graph here, again in black, this shows the amount of carbonate being produced by the different groups of corals at each of these sites. So the major frame builders, the Acropora, the Orbicella in the grey and the stripes, the opportunistics in the black. And you can see, just visually, really, that the opportunist species are contributing a very large proportion of the carbonate at most of the sites that we've looked at. So they dominate over the traditionally important frame builders, Acropora and Orbicella, at 46 of these 74 sites. And in terms of those key frame builders, Orbicella is still important at a number of sites, most important producer at 18 of 74 sites, but Acropora contributes to more than 20% at only 3 of the sites. So essentially it's really doing nothing in terms, at most sites, in terms of active carbonate production. And Acropora actually doesn't occur on most of the transects that we've looked at. The other interesting point to make about this data, and obviously realising this will stop tour through it, is that at a fairly significant number of these sites is actually things like branch parietes and various species of madrassis that are also making a fairly important contribution and are actually more important again than Acropora and Orbicella in terms of overall estimated rates of carbonate production, particularly actually at many of the sites in the sort of southeast of the Caribbean. So if you look at sort of St Lucia, St Vincent, Bonaire, at these sites we see very high relatively high cover of some of these kind of branch coral species, and they're also contributing reasonably large amounts of carbonate. Overall, there's a fairly good relationship between live coral cover and coral rates of carbonate production, as one perhaps might expect. And if you take the entire data set, there's a reasonably good relationship, interestingly here, between relative increases in the relative abundance of opportunistic species and then declining coral production rates. So the more opportunistic species you have, typically the lower the rates of carbonate production on the reef. So what I should actually say is that a lot of these kind of outliers are actually sites that have very, very high abundances of things like parietes and madrasses. So I was still working on this on the plane over on Friday, so we're kind of still working through what some of these what some of the data sets mean. But this is kind of the state of the data at the moment. I still need to pick out a little bit more from the data in terms of contributions from different opportunistic taxa to overall rates of production, but that'll be something I'm working on when I get back from this trip. So that's all quite interesting, because it points really to some fairly important changes. If these species become progressively more important on the reefs, then it has some profound implications in terms of overall production rates. The other thing we might think about briefly is, well, if production rates are so low, why have more widespread transitions to net erosional states not occurred? And that is, of course, because overall rates of biological erosion, remain very, very low in the Caribbean. They average only about 2G across all of the sites. Parrotfish remain the most important bioeroders at all of our sites, but rates, as I'll show you in a minute, in a historical context, which is shown across here, averaging between about, I can't even see that from here, about 1.5 down to about 0.8 in the deeper environments, are very, very low. And as far as we can tell, very low in a historical context. And urchins, of course, which haven't recovered, remain essentially functionally irrelevant in terms of any meaningful bioerosion in the region. It would be lovely to be able to draw on lots of interesting comparative historical data sets to compare bioerosion rates with, but there are very few to kind of go at in the literature. This is what I've been able to kind of put together in this context, and it shows relatively recent historical data, so data from, I can extract it from the 70s, but in some cases the late 1980s, early 1990s, in terms of rates of parrotfish bioerosion, urchin bioerosion and sponge bioerosion, compared to the sort of average rates that we see today. I'll come onto this part of the graph in a minute, but you can see that all of these the contemporary rates are much, much lower than those. I suspect that parrotfish bioerosion rates, if we went back 50, 60, maybe even more years, would be even higher than these figures suggest here. These are from some protected sites in Bonaire, but nonetheless there's still a fairly significant reduction. But if you add together those kind of recent historical estimates of urchin and parrotfish bioerosion, that would suggest that rates of perhaps at least 7 to 8 kilograms of calcium carbonate per year might have been being removed by biological erosion from the shallower reef sites. So current rates are at least 70% lower than that. And the interesting thing is that if you were to impose even these probably slightly lower historical rates onto the contemporary rates of production, most reefs would actually be in highly net negative states. So this transition has probably been to some extent mitigated by the fact that we've also lost an awful lot of the bioeroders in the region. So there's a sort of offset to some extent between losing a lot of coral production, but that being to some extent mitigated by major declines in a lot of the bioeroders. That's not to suggest, incidentally, that loss of bioeroders is a good thing. It's clearly not, but in terms of production regimes, I suspect it's having a bit of a bearing on what's going on at the moment. As to the future, briefly, well, one can play around with all sorts of different future trajectories for reefs in the region. This sort of cartoony plot here shows gross production declining from sort of pre-1980 states, erosion also declining, and then what this does in terms of net production. Contemporary reefs, which are shown in different states here, exist in different conditions. Some of the sites, such as in Bonaire, still retain reasonably good net production, positive production states. Many are close to zero, and a few have obviously started to move into net negative regimes. What will happen in the future? Well, it depends, of course, on the balance between rates of production and erosion. If one is a massive optimist, one might like to imagine ongoing recovery of Palmata and so on, which would increase production rates. Alternatively, we may have scenarios where production rates remain pretty much as they are now, and with these sort of short-lived, high-turnover species dominating on many reefs. Or indeed, things may get much worse, and so depending on the interplay between those, you can envisage different kind of trajectories for the future in terms of things either becoming a little bit better or staying the same and so on. And of course, integral to that will be what happens in terms of perhaps any recovery of diadema, protection of parrotfish populations and recovery of those and so on. We've done some preliminary attempts at sort of trying to model future budget trajectories. This is work done by a student that Pete Mumby and I supervised, Emma Kennedy. Many of you may know this work, that came out again last year, that looks at two different hypothetical Caribbean reefs with 10% and 20% coral cover, inside and outside managed reserves, and then is tied in with different climate change scenarios to build in kind of impacts of bleaching and acidification and so on. But really what you can draw from these preliminary modelling efforts is that most of those scenarios project a fairly bleak future for Caribbean reefs without very effective management and certainly fairly aggressive strategies in terms of CO2 emissions. What I would say about the modelling, I think it has an awful long way to go at the moment. There's a huge amount of literature emerging almost every week in terms of the impacts of ocean acidification and so on different taxa and different processes, and that work kind of clearly needs building as we develop these models a little bit further into the future, and that work's kind of ongoing at the moment. So many key questions remain. What are the long-term impacts of changing coral assemblage? The potential rise of the opportunist slow recovery of cropper if it really is happening. Further loss of orbicella in some of the areas where it remains important. Uncertainties in species and process responses to sea surface temperature, ocean acidification and so on. And I think how will the dynamics of reef bioerosion in terms of the species and rates change as habitat complexity itself continues to change. And so I think, just to conclude, I think there are some potentially quite interesting sort of feedbacks that we're starting to kind of work on now, given that the different substrate, or the ways in which bioerosion, different types of bioerosion utilise space within the reef environment and utilise live and dead substrates and so on. As those change, either rapidly, and one scenario that would become sort of disease die-off of Palmata that leaves a lot of the standing framework intact, but which perhaps over time declines, or a hurricane strike that very rapidly changes architectural complexity. That's likely to have impacts in terms of how bioerodes operate in these environments, with potential impacts and implications in terms of carbonate budgets and so on. So this is, I think, one of the sort of interesting areas that we're trying to sort of work on and push forward on at the moment. So I will leave it there and just thank the various people involved in the project. I'm not sure Pete ever thanks me for showing this particular picture, but and the various people that facilitated field and site access in the various places we work at. So thank you for your time, and hope that was of some interest.
Well, we've got time for questions. I don't know if anyone's at UQ, because we can't see you today, but have you got any questions for Chris? We'll start with you.
Any question? No, we're fine.
You're fine? All right. Okay. Does anyone in the audience here like to ask a question?
John.
Chris, I was just wondering about when you talk about the comparisons between the production rates in modern and looking at the accretion rates, and you mentioned that you thought it was conservative because of the transport, the modern transport of. But in reality, those fossil reefs would be undergoing those same offspring.
Yeah, no, what I'm saying is that our attempts to convert the modern rates to an accretion rate don't really factor. It's very difficult to come up with a sensible number to kind of remove from the contemporary rates. The fossil record obviously integrates that, and so those rates are what they are. Those are the rates at which the reefs accreted. The rates we've derived today, I think, are at the more optimistic end of the spectrum, because we haven't taken out perhaps periodic removal of carbonate from the contemporary conversion rate.
And what about the other sediments?
Yeah, that's my question.
The stuff that's...
Yeah. So at the moment, we it's a topic of ongoing, lengthy discussion. We haven't really come up with a sensible way at the moment of trying to come up with estimates of rates of sediment production on reefs. Largely because a lot of the rates of species turnover and so on are very, very variable, and they therefore bring in an enormous amount of error into any estimates that you come up with. My kind of, if I was guessing, I would say that production rates probably may well have actually increased, largely because I think you see so much halimeda everywhere in the Caribbean now.
But you always did,
Mm-hmm.
I mean,
well,
one of the things that bothers me about, I think this is very cool work, but on the healthy reefs of the early 1970s in Jamaica and whatever, what you're calling the opportunistic species were commonly 50% or 60% of the coral cover. Agaricids, platyporites, fingerporites, madracids were always a huge component of the system. But the other thing in relation to John's question is I spent a lot of time in sand channels because I was interested in end fauna and whatever. And if you ask the question what the source of the carbonate in a sand channel was between two beautifully healthy buttress reefs, I'd be willing to bet you that the vast majority of that sediment was not produced by corals.
No.
It was produced by various kinds of calcareous algae that don't even live on the reef, right? Or the halimeda that's sort of draped off of it. And if you look at dredge samples from sort of down reef, that integrated it all, it's very common to have 50% of the volume of the carbonate be halimeda alone.
Yeah. I mean, this is something that we obviously talked quite a lot with Bob about when we were away, and he talks at length about the very large amounts of acropora, halimeda that you used to find around
the reefs, right?
Yeah. And also around the bases of staghorn corals, and
they're producing those cornflakes at an incredible rate.
Yeah. So I wouldn't dispute that a lot of those so-called opportunistic species were clearly there. I think it's a question, their relative abundance has obviously increased. I'm not standing here saying that there's more of it in absolute terms because it's quite difficult at more than one or two sites. I mean, obviously Ed Green and people have done work, where they've tried to look at some of these changes in the past, but there aren't very many of these sites where you can go back and say with any confidence that the absolute abundance has increased.
Yeah, well, that's what we're doing now. They're like a dozen where you can.
Yeah.
It's not really clear to me how your measures of coral growth are translating into reef accretion or carbonate production. So when you were showing the three different pictures, it looked like, is that a linear extension estimate? And I know you've got to then account for depth.
Those account for both. So they're just examples to illustrate the fact that obviously branch corals have typically much higher extension rates than a massive coral.
So is your measure the total, when you talk about the carbonate budget, is your measure the total amount of carbonate that's produced by weight within a given area of the reef, or are you more interested in the rate at which the reef is growing?
No. The reef budget methodology, as we developed it, works out the amount, the weight, if you like, of carbonate. It's an estimate of the weight of carbonate produced per unit area of reef. So it's definitely not a figure that directly translates into an accretion rate.
Okay, so that's obviously important in terms of knowing the growth rate of those different corals. But how do you factor in the sort of vulnerability of those different corals? So, when Montastri is likely to stay in place, whereas Palmada is likely to broken up and get dispersed off reef.
Yeah. So it's a measure of what it measures what we see at a particular point in time. Okay. So it's not factoring for the fact that a cropper may come and go, and some of the more massive taxa may stay there. Those are sort of further complexities, I suppose, if you're trying to then translate this into a rate of accretion. And it ties into the point I was making to John, really, I suppose, that it's very difficult to kind of come up with sensible estimates of how much you might periodically have kind of stripped away from those reefs. Of course, I suppose in the Caribbean at the moment, the amount that you probably have removed after a cyclone strike is significantly reduced to what you might have seen removed if you went to some of those sites in the 70s or 60s, because there's obviously a lot less of the stuff that's most vulnerable and susceptible to kind of removal. So I think where we've tried to make these sorts of conversions, we're aware that there are complexities in terms of trying to make that. And sort of point I was trying to make, showing that graph.
Would it be any easier to do like in a lagoonal setting, like take your approach but expand it to the entire, but doing it in sort of like a sandy lagoonal setting to try to get? I mean, I don't know, just whether
to get at which
wouldn't the transition between production and accretion potentially be easier in a lagoonal situation with sediments? Where there's not a whole lot of. I'm just thinking about places like the middle of some of these GBR reefs. I know it's far across from the country, where there's not a whole lot of transport. There's basically just infilling. There's backfilling. Of the lagoons.
Yeah, maybe. Well, I guess I can't say I've never really thought about that, but I guess it's a sort of slightly different question, isn't it? Really, and you've got. Yeah, I mean, I guess you could get it. So you could probably, I guess you could come up with some average rates of sediment infilling and accumulation associated with those processes. But
I guess it's more difficult to get provenance on some of those things as well because they're so difficult to identify. The sand grains are so difficult to identify.
From all the sites you looked at, did you find, for reefs that were net eroding versus reefs that were accreting, any evidence that was translating into a similar pattern in shoreline erosion?
Not something that we've really looked at. No is the answer. I can't really give a firm indication on that.
Okay. Just one last question. Yeah, go on. I know at the end of the talk you were talking a little bit more about internal bioerosion. Is that going to figure more prominently in your future models? I mean, because a lot of that erosion happens at a level where you can't see it from the surveys, right?
Yeah.
The crack and whack approach is what we used to call it.
Yeah. So again, I think it's one of the in the Caribbean, where most of the bioerosion, in terms of the macroborers, is driven by sponges. I'm reasonably comfortable that we have we can make a reasonably good estimate of the kind of surface cover and so on. That becomes more problematic in the Indo-Pacific because we don't have any rates for lithophagous bioerosion, sulfur-included polychaete worm bioerosion and so on that we can use. So that figure is probably fairly conservative, I suspect. It's one of the things that we spend the most amount of time kind of grappling with, I think. And I don't think it's perfect, but it gives us a reasonable indication. As I say, you can't do anything with the micro end of this in the field. And we were deliberately trying to come up with a system that didn't require destructive sampling. So there are inevitably going to be kind of costs to that. I think applying some of the experimental rates that have been used and depth stratified rates that have been used is probably the best way to kind of deal with that.
Great. Okay. Join me in thanking Chris one more time.